Up to this point in the course, our main conceptual tool for understanding why objects move as they do has been the idea of a force. In this module and the next module, we're going to be developing a very different way of thinking about why objects move as they do. The bridge between the idea of a force and this new way of thinking about motion will be the idea of work. So in this video, I'm going to introduce you to the idea of work. So here's the idea. Let's say that we have a mass m, and that mass is going to move through a displacement. I indicate the displacement vector d. The idea is that the mass starts here and ends up here. We're going to say that as the mass is going through this displacement, a force is acting on the mass. And here is our force vector F. And we're going to say that there is an angle theta between the force vector and the displacement vector. So D vector represents the displacement, and F vector represents the force. Okay, so what is the work? We say that when a mass moves through a displacement while acted on by a force, the force does work on the mass. The work done by the force, given by the following formula. First, we use W to indicate the work done. That work done by that force is, by definition, the magnitude of the force vector times the magnitude of the displacement vector multiplied by the cosine of the angle between those two vectors. Work has its own unit. The unit of work is the joule. The symbol for joule is capital J. So joule is the unit of work, and we can see that work is equal to a force times a distance times cosine of an angle. So in order for our system of units to be consistent, the unit of work, which is joule, has to equal the unit of force, which is Newton, times the unit of distance, which is meters. The cosine is dimensionless, so we have then that a joule is equal to a Newton meter. Now, it's also useful to be able to relate any of our units back to the fundamental units, which are kilograms, meters, and seconds. So to get joules all the way back to kilograms, meters, and seconds, let's put in that a Newton is a kilogram times meter per second squared. Then we're multiplying by meters here. So we can relate a joule to the fundamental units by saying joule equals kilogram times meter squared over second squared. Now we'd like to get an idea of what work is all about, right? What is this definition of work here trying to get at? Now, a good way to try and start thinking about work is to look at what this formula is telling us in three different cases. Let's start by imagining that we have an acute angle between the force vector and the displacement vector. So I'm going to draw another figure over here illustrating a situation where we have an acute angle between the force vector and the displacement vector. This is already an acute angle, and I'm going to make a fresh figure anyway. Okay, so acute angle means that this angle theta is at least 0 and less than 90 degrees. Now let's ask ourselves if the work is positive, negative, or 0. Well, if we are bothering to compute the work, then that means that we probably have a force which is not 0, and we probably have a displacement which is not 0. In which case, the magnitude of the force would be a positive number, the magnitude of the displacement would be a positive number. So then the entire sign of work, whether it is positive, negative, or zero, will be determined by the cosine factor. Now over here, we are assuming that theta goes from 0 to 90 degrees. In other words, theta is an acute angle. Cosine of an acute angle is positive. And since the other factors are always going to be positive, that would mean work is positive. So in this situation here, angle between force vector and displacement vector is acute. That means that the work must be positive. Okay, now what do we learn from this? Well, we have a mass which is going to the right in this picture. We have an acute angle in here, and because this is an acute angle, that tells us that the force vector has a component pointing to the right. In other words, the mass is going to the right, the force vector has a component going to the right, the force is helping the mass to get where it's going, it does positive work. So that would be the first case. Now let's look at the case where the angle between the force vector and the displacement vector is 90 degrees. So here's our displacement vector. We're going to say that our force vector is at a right angle to the displacement vector. So our theta here is 90 degrees. All right, is the work positive, negative, or zero? Well, if theta is 90 degrees, cosine of theta is then zero, so the work would be zero. Okay, so what is this telling us? Well, the mass is going to the right. The force does not have a rightward component, so the force is not helping the mass to get where it's going. But on the other hand, the force does not have a leftward component either. It is not opposing the motion. So in this situation, with a right angle between the displacement vector and the force vector, the force is just neutrally pointing off to the side. It does zero work. Okay, one more case to go. We want to look at the situation where this angle between the force vector and the displacement vector is obtuse. Okay, here's our mass going through a displacement again. And this time we're going to have an obtuse angle between the force vector and the displacement vector. In other words, theta is greater than 90, no greater than 180 degrees. In this case, is the work positive, negative, or zero? Again, magnitude of the force vector is going to be positive if we're bothering to compute the work at all. Same for magnitude of the displacement vector. The sign of the work, positive, negative, or zero, is determined by the cosine factor. And if this is an obtuse angle, cosine will be negative, so the work will be negative. Okay, so what is happening in this case? Well, again, I have drawn the mass going to the right. In this case, the force has a leftward component. So the mass is going to the right. The force has a component opposing the motion. It is doing negative work. Okay, so when the force is helping, it does positive work. When it's neutrally pointing off to the side, it does zero work. When it is opposing the motion, it does negative work. In the next video, we're going to be doing some practice calculations involving the work.